Hello, everybody. So we want to talk about recurrent neural network. So we will start, maybe start today. So, first we need to know what is the difference between recurrent neural network and, for example, feed-forward neural network and MLP, multi-layer perceptron, CNN, because CNN also it's a kind of feed-forward neural network. So what is the difference between RNN and feed-forward neural network? So first, we need to see the limitations of feed-forward neural network. So it can only handle fixed input size. So this is a problem, in fact. So for example, if you have an image and you want to classify this image into A and P, if it is cats and dogs and you want to classify it, the input volume must have fixed input size. This is very important because it is connected with weights. So we have the input layer, and the input layer will transfer inputs into the maybe first hidden layer and so on. So it's very important that the input should have a fixed size. If it does not have fixed size, we can fix this by using zero padding, for example. Um, so for example, and also we can, so if the input is small, if the input is the size of the input is less than the actual size, so for example, you can use zero padding. You can add some zeros to just make it equivalent to the actual size, and we can work with it. If it is more, we can cut some parts, right? So if it is more than the actual size, maybe we can remove some parts from the input. So just imagine that you have a model. As this model has 20 inputs, and at the moment you have only 15, for example. So in this case, we can use zero padding. We can add zeros for the other 5 inputs. So the input must be has this kind of fixed size all time. If it is more, if it is 22 pixels, for example, and it should be 20. So in this case, maybe we can remove 2 pixels from left or from right, for example. So this is how we deal with. This is how feed-forward neural network deal with the size of input volume. So the model breaks down when the input exceeds the fixed input size. If the input size will be different, the model will break down. So the model size dynamically grows with the size of the input sequence. So if the input sequence will increase, of course the model capacity will increase because number of weights will increase. So the model will increase as well, or it will grow with the size of the input sequence. In case of, for example, CNN, we don't need this kind of data preparation. But in RNN, we have a kind of preparation, but it's something else. But from this point of view, we can just say that maybe CNN models, they can work with raw data as it is. So one big limitations of feed-forward neural network is that it cannot capture long-range dependencies between input vectors. So imagine that you have an input sequence or a sentence, and we need to use feed-forward neural network to translate it, to classify it for sentiment analysis, whatever. So if the input will be a sequence, and if the feed-forward neural network has a fixed input size, so you can just imagine that um, we will move across the input from left to right with some with a fixed input window, for example. So I can process one part, move, process another part, and so on. So we can scan the input size from left to right using fixed input size. But in this case, the model also does not have a memory. I mean, feed-forward neural network, it does not have a memory, so it will not remember what has been done before. I mean, there is no any way to capture those long-range dependencies between input vectors. So if you have, we use flatten, for example, and if you have a large input vector, and this input vector, we will divide it into small pieces, and each pieces will be fed into a feed-forward neural network, one at a time, for example. So in this case, it will be discrete. So we can deal with the input sequence, but we will not be able to capture the long-term dependencies between input vectors, between those sub vectors. Because feed-forward neural network, it does not have a memory. So it will not be able to remember the context, in fact, or dependencies between input vectors. So this example, this is a feed-forward neural network, and it has fixed input size because this is how we know it. You can use this one for regression. We can use it for classification. Imagine that we can use this one for sentiment analysis, for example. So maybe the input size here will be a text, and the text, it could be a sentence, right? So we talked before about this internet database for movies, and the people write reviews. Some reviews are longer, some reviews are shorter, and if we can, we need to select maybe the most important words or characters, for example, and we can use those for as an input, for example. And in this case, we can use feed-forward neural network for sentiment analysis. So, for example, I watch a movie, I will write one sentence. Maybe Ali, he will watch a movie, he will write long, maybe one A4 page, for example. So the size will be different. So the one who is designing the system, he should decide what will be the input volume size. And if my one is too short, we will use zero padding to fill in other inputs by zeros, and we will use the model as it is. So if it's fixed input size, and if all inputs are available, so it will be the first case. If the input size is less than, if the input sequence is less than, or the input vector is less than the input size, in this case we will use zero padding. So some part will come from the input, and the rest we will use zero padding here because I need to have input fixed input size. So in this case we will use zero padding. In the same way, if it is longer, for example, what will happen? If it is longer, so we will cut some parts. So you can just say that I will truncate that part from the left side. We will ignore that part, right? So if the input vector is larger than the input size, in this case we will just ignore that part. We will say, okay, this part we will ignore it, which might be a problem. I mean, should we ignore the part to the left or to the right? This is a problem. But usually people start from left to right, and in this case we will ignore that part in the right-hand side. But the problem in feed-forward neural network, we don't have a memory. So when the model processes this input vector, it will process it. And when you give it another vector, for example, in the sequence, the next vector in the sequence, it will not memorize what has been done before, in fact, because it does not have a memory. The problem, lots of problems, it's not sequence to sequence, in fact, but you can just say sequence. Sequence to sequence, it means the input is a sequence and the output is a sequence. For example, in machine translation, I have an input sentence, and I want to translate it from Norwegian, for example, from Norwegian into English. So the input is a sequence, and the output will be a sequence. Maybe the size will be different. So it requires to move from left to right reading of the input sequence. We need to move from left to right. We need to update the state vector incrementally. This one is wrong. In fact, to represent the semantic, and the discourse context from the beginning until the current input. So we call it context discourse will be broken in case of MLP and CNN. So if you have an input sequence, and we need to scan this input sequence from left to right, if you will use MLB, what will happen? I will start scanning maybe this part. If the input size is 3, for example, so I will scan that part first, and after that I will move to the second part, and after that I will go to the third part, this part, and so on. So we will move like this one. It will be like this one. So we will scan the input sequence from left to right, and each time when we scan an input part, in fact, we need to memorize something. We need to update something to know what has been done, right? Because I have some input sequence, and I will, for example, when you are writing in Word, for example, sometimes you discover that the Word will mark some words by red when it's wrong, which means it can't understand something about the history. Maybe it's a grammar, right? Maybe something else. So in this case, we need, if you will use multi-layer perceptron, or if you will use MLP, I will scan that part, I will process it, I will move to the second part, I will process it, I will go to the third part, I will process it. In MLP and the CNN, we don't have this kind of memory to remember the context. What is the context to discourse? What is the semantic from the beginning until the current input. So this is a problem in MLB and CNN. This context discourse, it will be broken in MLB and CNN. So we need to integrate the current input into a state. We need to develop something different. We need to keep a state. We need to update. We need to have a state, and this state, we need to update this state each time when we have some different input sequence. And this state, in fact, it will represent, it will work as a memory, which will allow pattern to be remembered for over long range context. So each time when we have some input vector, for example, I will update my states. I go to the next input. I will update my states also, but I have the historical state from last sequence. So this historical state, it should remember something about the context. So in this case, we need to develop something different, not MLP, not CNN. We need to have a kind of recurrent. We need to update a state, and this state will work as a memory, which will allow the model to remember over long range context. This is very, very important. So for example, in sentiment analysis, maybe I have a text, and this text, I want to classify it into positive and negative, right? So I need the output to be maybe positive and negative. It could be +1 or -1 or 0, for example. So I can deal with the sequence as one package, as one input volume. So you can deal with it as one input volume, and the model will directly classify it into positive and negative, for example. But in case of RNN, or recurrent neural network, we will scan this input sequence step by step or part by part. So we need to break down the input sequence into maybe sub-vectors, and then we will scan the input text from left to right. And in this case, we will have an advantage here that there is no dependence between the size of my model, the size of the model and the size of the text. Because if you are working with MLP, for example, if the input volume, imagine that you are working with a text, and this text has a size of 200 characters, for example, 200. So in this case, the input volume will be 200. If it is more than 200, we need to use zero padding. Sorry, if it is less than 200, we need to use zero padding, because I cannot work with unfixed input, because in MLB and CNN, we are working with fixed input size. So I must keep this fixed input size all time. So if the input sequence is less than the actual size, we need to use zero padding. If it is more, we need to cut those more pixels or more information or more variables, and we will move from left to right. So we will cut the extra ones which are on the right hand side. If you need to increase the volume size, your model will increase. I mean, the size of your model will increase, and when the model size will increase, you have chances to overfit, right? Because the model capacity will increase also. So this is a big problem. So imagine that I'm doing this sentiment analysis for movies reviews, for example, and I will work with 200 characters, like in Twitter, for example. I don't know how many characters in Twitter. How many? It's fixed. So we will use this fixed size. If you want to increase this size, in fact, you need to process your data because it needs some processing, and the model size will increase as well. And when the model size will increase, chances to overfit will increase. So this is a problem. So this is a problem in MLB and CNN. If you will increase the input volume, the input size, the model capacity will increase. And then when the model capacity will increase, maybe the model will overfit. Chances will be very high to overfit. But in case of, we need to find a different type of models which can overcome this problem. And what are the problems? Number one, I need to scan a sequence or an input sequence from left to right, and I need my model to be not dependent on the input size, the size of the input size. I need to scan it, just scanning it. So I will scan it several times. I will scan. So I don't care about the size of the input volume. If we will use machine translation, someone is talking, and I want to convert this text or speech, for example, from one language to another language. I don't know how the length of the sentence. Maybe someone, he will give short sentences, someone will give longer sentences. So if I need to translate, if I need to build a model for machine translation, I need to build a system which is independent of the size of the input sequence. How can we do this? Using recurrent, because recurrent it will scan the input sequence maybe part by part and update the model parameters, share the model parameters between different steps or different time steps. So when we share the model parameters, we will have a fixed size or fixed number of parameters, regardless of the input of the size of the input volume. So I will scan, and each scan I will update the model parameters, but I will not touch the structure of the model. The structure of the model will be fixed all time. So we don't need to increase the input volume. We don't need to change to increase the number of weights and bias. So the model size will be the same all time, regardless of the size of the input sequence. This is very, very important advantage. The second advantage also, it's the state. I need to keep the context for long time. I need to understand the context of the text. Because when you are talking about a movie, maybe at the beginning you are negative and after that you become positive. So if I will use the last impression, maybe it will be positive, but you are being criticizing the movie, or in the whole discussion you are being criticizing, and using sentiment analysis, your view should be negative, not positive. But you are just talking negative, 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 and at the end you said something positive. So if I'm using MLB, in fact, it will be positive, which is wrong, because it will just use the last input sequence, which is positive, and it will forget about the context of what has been done before. But if you are using RNN, in fact, we will keep this long time dependency or context, long range context with us. How can we keep it? Using the state. So we will have a state, and this state we will update it each time, and we will keep updating it. And at the end, we will calculate the output as a function of the input and the state. So the state is very important. The state will be the memory which will remember or memorize this long range context from the input sequence. So we will come to this RNN, recurrent neural network. So RNN was first introduced in 1980. So in fact, it's very, very old, from 1980, but it has gained popularity only recently due to the hardware development that have made them tractable to train. We had those from 1980, but it was hard to train those models. So it was not practical. And it's the same when they developed the perceptron, for example. They used the perceptron in some applications, but they discovered that the perceptron has very limited capacity, and we cannot use it for maybe more difficult, more complex problems. And they stopped at that point. So it's the same. They started this RNN in 1980, but because of hardware restrictions, they couldn't train those models as today, for example. So today, it gained more popularity today because we have more computational resources, and it should be possible now to train those models more efficiently. So RNN are different from feed-forward neural network because of recurrent layer. Because of this, we have this kind of recurrent layer. Each time we calculate a state, in fact, based on the input and the previous state. So this one, we calculate a state, I will call it HT, based on XT, the current input, and the previous state, which is HT minus 1. So we keep updating this state, and this state will represent the memory in my model. This one will be the memory, which will remember something about the context of the discussion or the text and so on. So RNN are different from feed-forward neural network because of the recurrent layers that enable it to propagate information between neurons of the same layer and maintain a state between uses of the network. So we have here the multi-layer perceptron. And multi-layer perceptron, in fact, we move from left to right. We have an input fixed size. I mean, the input should be has a fixed size. And we have some number of layers. We feed inputs from one layer to another layer, and until we have the outputs or conclusions. So this is the feed-forward neural network. But in case of, so you can just say that we have time steps in RNN, but in case of layers, we are moving in the space from, so we have a space, not time steps, space. We are moving from left to right for calculating the outputs, but in case of recurrent neural network, we can expand it over time steps. We can unfold it over time steps. So we are working with the time domain here. It's not the space. So just very simple here. I need to calculate the states. The state will be ht, and how can we calculate it? It will be a function of ht minus 1 and xt. But and it's recurrent neural network, recurrent layer. So how can we calculate it? This is a very simple function. In fact, it's omega x multiplied by x. Omega, it's the weights. So it's omega x multiplied by x plus omega h multiplied by h, by states, plus bias. And we will apply activation function to calculate the states. So now in this case we will get states. So for each, so if you have an input sequence, we will start with be the first part. You will decide this one. It's user defined. So you will decide the size of the input vector. We will consume that part. We will calculate ht, right? And after that, we will go to the second part. We will update ht, so we will get ht plus 1, and so on until we are at the end. And each time you update the states and you calculate the output, but maybe the last output will be the most important for us. So in this case, I can just divide the sequence into small parts, and I will scan the input sequence, and each time I will update the states. So there is very simple RNN model called vanilla RNN, and this vanilla RNN model uses standard perceptron layer. It's just very simple, similar to perceptron layer with nonlinear activation function. This nonlinear activation function, they use, in fact, hyperbolic tangent. So they use this nonlinear activation function. It uses here 10H, hyperbolic tangent. So vanilla RNN model uses standard perceptron layer with nonlinear activation to achieve recurrent state input combination function. It's combination because we combine the states with the input. We have state input combination. So here in this, when we calculate the states, in fact, we update the states by combining the current input with the previous state. There are several variants of RNN with a stronger representation power. Vanilla RNN calculates an output sequence. It calculates an output sequence. For example, H1, H2, Hn. What is n here, in fact? It's when you have an input sequence, you will divide it into n sub-sequences, for example. Or if I have an input and I want to scan it, so how many time steps required to scan an input sequence or an input sentence? So n will be this number of scans, for example, given an input sequence x1 and until xn, for example, from the initial state, using the initial state h0. So because at some point we need to start from some starting point, like an incentive. So what will be the starting point? It will be the initial state h0, and this initial state, and all the states are calculated according to the previous state ht minus 1 and the current input xt. So the function will be like this one. RNN step, we update ht, or we calculate ht based on the current input xt and the previous state ht minus 1. So this is the only equation which we have here for updating ht. And because we have this recurrent, if you have this recurrent, it means I will calculate the states and I will feed it back into itself again, to the same neural network one more time. Just to have this feedback loop to feedback the previous state into the new updates of the new state. And it will be done using this simple function. It will be omega h multiplied by ht minus 1. So omega h, this is weights. So it's a perceptron. It's based on the perceptron. So this perceptron, we will have a perceptron called state, for example, or wh. We will have the wh multiplied by ht minus 1 plus wx multiplied by x plus bias. And the f will be the activation function. This one will be the nonlinear activation function, which is hyperbolic tangent here. Omega h, omega x, and b are the model parameters shared among different steps. So we will have only one copy of omega h and omega x and bh, and those model parameters will be shared among each different time steps. So if we need to unfold it, so RNN looks very different from MLB and CNN due to the recurrent time steps. So we have this kind of recurrent. You can just say, I mean, long time ago, we have this kind of delay time. So it should be possible to add something like this triangle here, which means the output is one time delayed than the input. It's something like this one. So this is the RNN. We will have the input using the input and using the initial state here. If you are starting now from the left, extreme left, we will not have any states. So usually we start from initial state H0, and this initial state can be initialized into 0 or some random values, right? You need to start from somewhere. So you can just say, okay, my initial state is 0 or just small random number. We will use xt and ht-1 for calculating or updating the state ht. And if you want to calculate the output, in fact, the output also will be a function of, I mean, a function of the state. So it will be like another perceptron. So W will be omega W multiplied by, or W multiplied by H plus BH. So it will be another perceptron. So MLP, the output from lower layer is fed as an input to the upper layer. I put this one in this form to be look like RNN. This one is RNN, this one MLB, right? So do you see the difference between both of them? So you can just say that in MLB, the output from lower layer is fed as an input to the upper layer. It will be like, we will move like this one, from bottom to top. So this is MLB, this one it's MLP. This one it's RNN. I just try to put them in the same way to make good comparison. So the output from one layer will feed into the upper layer. So I have this input layer. It will feed the input to the upper layer, which is the first hidden layer. The output from the first hidden layer, it will feed it to the second, to the upper layer, which is the second hidden layer, and so on, until we calculate the output in MLP. In case of RNN, the output of a network layer is wired back as an input to itself. So the output from this layer, in fact, we will feed it back into the input to the layer itself. We will have this kind of recurrent or kind of feedback. So in this case, we will have the state, and this state, in fact, it will memorize something about the history. It will memorize something about the context. If we need to unfold RNN, so if we don't wipe away the previous state ht-1 when calculating ht, but instead record all the historical values or history states, we can effectively unfold the recurrent state transition process into a linear chain. I need to understand how can we convert this one into this one. This is the original RNN. This is unfolded RNN. Over time steps, in fact. It's not physically. It will not be like this in real time or in physics. But this is the model in physics. We have a perceptron, and the output from this perceptron, we will feed it back into itself again. So we have this kind of feedback. So this is my model. What are the model parameters here? Model parameters here are WX and also WH here. We will have here WH and the bias, plus bias. Those are the model parameters and the bias. So it's like a perceptron where we feed back the output into the input again. So each time we will have this perceptron, and this perceptron will have two inputs, X and ht-1, and we will use model parameters, which is WX, WH bias, to calculate H using nonlinear activation function, which is hyperbolic tangent. So this is this vanilla RNN. If you want to unfold, if you need to write it as an equation, for example, we can say that Hn will be RNN underscore step of, as a function, it will be calculated as a function of xt and ht-1 previous state using this kind of equation. This is the mathematics of RNN, where f will be the activation function. It could be hyperbolic, it could be ReLU, it's up to you, right? But usually here it will be hyperbolic tangent in vanilla RNN. So, and the model parameters here, what will be the model parameters? The model parameters will be omega h, omega x, bh. If we need to unfold it, so just imagine that we will keep each value. We will break down this feedback. we will break down this feedback line here, feedback loop, and if I want to calculate ht minus 1, how can we calculate it? If I want to calculate ht minus 1 using ht minus 2, right? Or if we are starting from here, it could be h0, right? And the xt minus 1. So I will calculate those values using omega h, omega x, and bh to calculate ht minus 1. So this is one time step. So just imagine that we are at t minus 1 time step. So if we are at t minus 1 time step, so it will be like this one. We have here t, we have here t minus 1, we have here t plus 1. If we are at this step, what should we do? I should get ht minus 2, and I should get xt minus 1, and use those for calculating ht minus 1. I did that, and I calculated ht minus 1. So this is over time. So this one will be the time scale or time horizon, for example. So at that time step, imagine that we are starting here. If I'm here, I need to get ht minus 2. I need to get xt minus 1 to calculate or to update ht minus 1. Now we did it. So I will not feedback. I will not use a feedback loop. So now I have here ht minus 1. I will use ht minus 1 and xt to calculate ht. Correct? And after that, I will use ht and xt plus 1 to calculate ht minus plus 1, and so on. Right? So we don't have 3 layers. We have only 1 layer, in fact. But we will run it. We will make those updates in a for loop. Imagine that we are doing this 3 times. We update the states 3 times each time. So when we unfold it, it means we try to unfold it as a chain, linear chain, over time. But in reality, it's only one perceptron with 1 set of parameters. So we don't have new parameters each time. We just update those parameters each time. Right? So now if you have a time series, and if you want to look into if you have a time series, and we will divide this time series into like windows. The size of the window will be maybe 3 values or 4 values. So we will use 3 or 4 values to predict the next value, right? And according to the size of the input, right? So if you have 4 values in each time, in this time window, you have 4 values. It means we will run RNN 4 times in each time window. Right? So I hope that you understand what I mean. Yes. So the steps can then be written as, those steps can be written this one. So we will have the H capital, which is a vector of states. It will have those states if we are storing them over time. So we will have H1, H2, and Hn. So in fact, RNN, each time it will calculate those states. So the initial hidden state H0 can be set to 0, or can be defined as a randomly initialized parameter. We can initialize it by random number. We can just set it to 0. So, and at the end, we will calculate Hn. At the end, the final vector Hn can be used for representing the whole set of inputs, the whole sequence of inputs, right? So now I have an input sequence, and this input sequence, it's an input parameters. So imagine that the window size, if we set n equals 3, for example, right? So when n equal 1 for the first input, I will use the first input x1, and I will use the initial state, which h0, to calculate h1. When n equal 2, I will use h1 and x2 for calculating h2. And after that, I will use h2 and x3 for calculating h3. So now, in fact, h3 includes all information because it's memory. The state is a memory. So in fact, it's h3 now. It knows all information about all historical values, or it can be used for representing all inputs, which is x1, x2, and x3. So now we have the context. We have long-term, long-range dependencies. We can memorize it. So we don't need to use, I don't use to use h1 and h2, those states, initial intermediate values. I don't need, in fact. We just need to have the final state, which is h3. Now h3 will understand or will memorize something about the context of x1, x2, x3. And we will repeat this one each time. So this is the window size. So in fact, n here represents number of inputs which will be used each time for predicting, for example, yn, or so I'm using x1, x2, xn for predicting yn, right? How can we do this? We need first to calculate hn, and after calculating hn, you can predict, for example, yn. RNN are trained using unfolded representation using backpropagation through time. We use backpropagation, but it's different strategy for backpropagation. It's something over time, so they call it backpropagation through time, BPTT. The training is identical to MLP, except that the number of layers is dynamic to the input and they can be large. Number of layers, because when we unfold it, in fact, you can just, we converted it into this chain of layers. So the number of layers here, in fact, will be identical to the number of input, right? So this number of layers will be dependent on the number of inputs. If you have long sequence, it will be longer. If you have short sequence, it will be short. So it's dynamic. You don't need to define it, in fact, because it will be a for loop. I mean, we will go through the input sequence n times, or imagine that we have a for loop, and using this for loop, we will adjust. We will calculate the states n times for each input sequence. And the n will be dependent on the size of the input sequence. But in reality, in fact, it is the original size, which is a perceptron. But this perceptron, we will adjust it n times according to the number of input sequence. So the training is identical to MLP, except that number of layers is dynamic to the input and they can be large. RNN are subjected to gradient exploding and vanishing problem. This is a problem here, gradient exploding and the gradient vanishing or vanishing problem. So this is a big problem in vanilla RNN, for example, and therefore they try to develop new forms which can perform better in, like LSTM, for example. So it has a problem, RNN usually, it has a problem of vanishing gradient and exploding gradient. So
can I ask a question?
Yes.
Before?
Yes.
In this case, is the number of parameters like the weights and biases the same as in the normal MLP?
No, it's the same structure, but we have this kind of feedback, recurrent feedback. Except
yeah, but when it comes to the hyperparameters, like to the weights of in each layer and the bias, is it the same as it would have been in MLP, in addition to the fact that we are like having this loop?
Yes, we calculate it in the same way.
Okay.
But just as the equation, just remember the equation is different. So if we can go back to this equation, so how many parameters here? So we will have here omega h, omega. So in each step, so to just update the states, how many parameters? It will not be omega h plus p. No, it will be omega h plus omega x plus p. So just go back to the equation to understand how many parameters in each time step. So it's a perceptron, but the structure of the perceptron is different because we have feedback loop. We feedback the states into the input again each time.
So we have more parameters, right?
We have more parameters.
Because we, okay, thanks.
Yes. But it's more parameters, but it will be fixed parameter regardless of the input sequence, because we scan the input sequence from left to right. So it has this difference between RNN and MLP, because in MLP, if you need to handle sequence of input which is extended or becoming large, I need to change the model, and the model will grow up. So the number of parameters in my model will increase according to the size of the input volume. But in case of RNN, it's independent, right? It will be just number of scans. I build a model, and it will just scan the input sequence, and it will memorize what has been done before using the states. So maybe the number of updates here will be just more number of updates, number of calculations will be more compared to MLP, because in MLP we have this parallel calculations. So I will feed back the inputs, and we will get the output. We will use this advantage of parallel computation, for example. But in case of RNN, we will scan the input sequence like in a time window, one by one, right? And each time we will update the states, and the current state we will represent all the previous outputs. So if you are talking, for example, if you have machine translation and someone just is talking maybe from 20 minutes, so we will update the states each time, and the last state we will represent the context from the beginning, from time 0, for example. Someone is right. Yes, Ali, you have. You shared a link, Ali. So okay.
Yeah, I just wanted to show the.
Okay. Yeah, this is very nice. Yes, when we unfold it over time. Yes, this is very nice. Maybe I will add this one to my slides.
Yeah, I just because I wanted to know that what's after this H parameters, so I search and find this.
Yes, yes. When we unfold it, in fact, as you can see here, I don't know if I can share this one with. So Ali, he was sharing this slide, this picture. Can you see it? So this is the RNN model. We have this kind of feedback, right, in the hidden layer. So using xt and the ht minus 1, we can calculate ht, or we can update ht. And once we have ht, we can calculate the output, right? So how we will unfold it or unroll it, in fact, so it's according to the size of the input sequence, and we will run it. We will unfold it over time like this one. So imagine that you have a time window of 5, for example. So I use the last 5 values for calculating, for predicting. So for example, I use the temperature of last 5 days for predicting today temperature, for example. So we will start at some point. We will initialize the state by 0 at the beginning, and I will use the first value, calculating or updating ht or h. It will be h1, for example. Using h1 and x2, I will calculate h2. Using h2 and x3 to calculate h or update h3, and so on until we at the last at hn we have hn. Once you have hn, this hn or h5, it will represent all previous values, x5, x4, x3, x2, x1, right? And we will use this last value for calculating the output here, because this is the one which I want to predict. I don't.
Can I add something?
Yes.
It's like the RNN is like some feed-forward network with a Markov chain, because it has some kind of memory.
Yes. Yes.
And in this network specifically, in this network, we only have one memory, right? One like.
Yes, the state.
Yeah, one state. We could add more states.
Yes, of course. Yes.
Thank you.
Yes. Thank you. So we will go back again to those slides. So yes. So when we unfold it, we will just use the final vector, state vector, which is hn, because this is the most updated one. In fact, when it's hn, it's the last update or the most updated one. And this one, in fact, it has all information about previous inputs from x1 to xn. RNN are trained using unfolded representation using backpropagation through time, and the training is identical to MLP, except the number of layers is dynamic to the input and can be large. RNN are subject to gradient exploding and gradient vanishing problems. This is a problem. So if you can see that this is a canonical form, this one it's a canonical form of RNN. This is unrolled or unfolded form over time, right? So each time we calculate ht using ht minus 1 and xt to update the states to calculate ht plus 1. And if you want to calculate the output, so it's easy. I mean, yt will be a function of ht. So x is input, h and y is the output. Yes, I just, can I answer the So sorry, I got a phone call from Mingitao, but it's fine. Yes. So this is the model, and the model parameters. The trick of RNN achieving dynamic size is the sharing of the model parameters across layers. So we have this omega h, omega x, and the bias. So we have this omega h. This is the weights, which are used to. I mean, we'll multiply these weights by the states. Omega x will be multiplied by the input, and this is the bias of the hidden layer, the state hidden layer, pH. So those models, I mean the trick here is that we are running this one over time, but we are sharing those weights between different steps over time, right? So it will be the same model, the same parameters, but each time step we will adjust those weights. So in fact, we are adjusting or updating the weights each time, and that is it until we calculate the final state which we want, which is HN, for example. So so the difference between RNN and MLB is that the size of MLB will increase with the increase of the size of the input sequence. But in case of RNN, we will not have this kind of problems. Why? Because we will have this trick of sharing those model parameters between time steps across layers. So the current input at any given time t is the combination of the input xt and the state ht minus 1. We know this.
Is that input or state?
Which one?
The current state at any given time t, right?
Yes, the current input at the current state at any given time t is a combination of the this is the current state. Yes, this is good. This one is. Yes, I will adjust it in my files. I uploaded it already to Blackboard, but I will update it and I will replace it with the last version. So the recurrent connection allows the network to remember what is learned in the previous step. The unrolled RNN graph can be imagined as how the recurrent connection flows from one step to another, allowing RNN cell to exhibit its memory-like characteristics. RNN can memorize previous inputs due to their internal memory for previous states. Training RNN is usually done one step at a time. So we do each step one step each time. So it's like we are running it in a forklift. So the mass of RNN, it's just the same. So we update the states for the hidden states. We update the states using some activation function here. So the input will be omega x multiplied by x plus omega h multiplied by ht minus 1 plus bias. And we need to calculate the output, which may be the probability of the next character. It could be the probability. So when you are typing, for example, in Word, you are typing maybe your something, a verb, for example, play. So when you type BLA, it should expect the fourth character, for example. So in this case, we can use a softmax, because if you want to predict the probability, in this case, we can just use softmax max layer. So the output, we will use the activation function softmax. So how can we calculate the output? It will be WY multiplied by HT, the last state, plus BY. So those are the two equations which are used for calculating the states and the output of RNN.
Hello, can I ask one question?
Yes.
If we have, for example, 3 features for each time step, so does that mean that we have 3 different states for each features?
Yes, I have an example. In fact, yes, you have 3 states, but which state you want to use, right?
For example, in the case of what I'm doing now for PV forecasting, we have input data for irradiance, for example, temperature, and some other parameters which are measured at the same time. So
yes,
maybe I can answer this question.
Yes, please.
Yeah, so I'm also doing the same LSTM forecasting work. So right now, when you see xt minus 1, xt plus 1, so that can be either a single number. It can be a 1D matrix. It can be a 2D matrix. It doesn't matter. So
it could be one vector.
Yeah. So when there are a number of features, so those features become 1D matrix. So then the xt minus 1 xt and all of that input becomes a matrix. So the features don't have an effect on the way x, u, and h works. So h will become a 1D matrix if the inputs is a 1D matrix.
And it will be a vector if the input is a vector.
Yes, exactly.
Yes, this is very good.
Thank you.
But so I was waiting for this kind of presentation, but maybe now I can show you someday later, not today, the way my LSTM is working. I've almost finished it. So
Okay.
maybe that can help a lot to people who are working with sequence to sequence forecasting in the class.
Yeah.
So can we have it next week, for example?
Yeah.
Okay.
Yeah.
And if we can share it in Blackboard as well, it will be very good. So if you can try to add more examples and explanations, so we can add it to the course contents, or we can upload it to Blackboard.
Yeah.
So so it's just, I mean, this comparison to feed-forward neural network. I mean, this is a simplified representation of feed-forward. So we have some input layers, some hidden layers, some output layers. So I just try to show you that it looks like recurrent. I mean, there is no big difference. In fact, feed-forward neural network allow information to flow only in the forward direction from input nodes through hidden layers and to the output. In feed-forward neural network, the decisions are based on the current input. It does not memorize past data, and there is no future scope. So, I mean, we make decision here based on the current input at the moment. But in case of RNN, we can have this memory by updating the states. Feed-forward are used for general regression and declassification problems. Feed-forward cannot handle sequential data. Consider only the current input, cannot memorize previous inputs. In fact, we can handle sequential data, but we will not have this kind of memory, right? So it will be a problem. Applications of RNN, it could be for image captioning, for example, it's one-to-many. So in this case, I have an input image, and the output image will be a sentence describing this image. So in this case, we can call it one-to-many. So the input volume will be 3D and will be 2D matrix, for example, or RGB image, and the output will be many, which will be a sequence of text or letters or characters. Time series prediction, which is one-to-one or one-to-many, in fact, right? So a window of values, it could be a window of values to one, so which is sequence to one, for example. So I can use a window of values or a vector of inputs to predict a single value, which is temperature tomorrow or stock market price tomorrow, whatever. In natural language processing, it's like, for example, sentiment analysis, and it's many-to-one sentiment analysis. The input will be a matrix, 2D matrix, which is a bunch of letters or characters, whatever, and the output will be maybe positive, negative. So it's many-to-one. Machine translation, translate input into different languages. So we call it many-to-many, right? We call it many-to-many because the input is a sequence and the output is a sequence. So one-to-one RNN, in fact, we can use this vanilla neural network, for example, and it's used for general machine learning problems that has a single input and a single output. We use today or current stock price to predict tomorrow future price, for example. So we can just use today value for predicting tomorrow value, right? So we have single input and we have single output. We call it one-to-one. Image captioning. So the input will be an image and the output will be a sentence. So it's one-to-many, right? We call it one-to-many. Or single input, multi-outputs, for example. So it will look like this one. So the input here, the input volume here will be an image, and the output will be, for example, many or multiple outputs. Maybe this is the length of the sentence which you are expecting to get from this neural network, from this RNN model, for example. So single input, multi-outputs. Sentiment analysis, it's multi-input, single output, because the input is a sentence, right? So it's multiple inputs, multiple words, for example, and the output will be just one and the plus one and the negative one. So in this case, it's multiple inputs, single output, or it's many-to-one. So for example, when it rains look for rainbows. When it's dark, look for stars. So it's a very positive sentiment. It's just a very positive view. Other people maybe they feel it dark and too much rain sitting at home, so it's negative. So this one it's positive sentiment. So in this case, the input is many, and the output is 1. So RNN takes a sequence of inputs and generates a single output. In sentiment analysis, a given sentence can be classified as positive or negative sentiments. In machine translation, it's multiple input, multiple outputs. So you have an input sequence or a sentence, and the output will be an input sequence or a sentence, an output sequence or a sentence in different language. For example, we can use this one for machine translation. So maybe translating from Norwegian to English, for example, and vice versa, right? So in this one, it's many to many, or sequence to sequence. A vanishing gradient problem. I mean, as I told you, in RNN we have this vanishing gradient, and it's exploding gradient. And it's about weights. So sometimes those weight values, it becomes very, very small, or a partial error by partial weight, it will be the gradient will be very, very small value, and at some point my model will not be able to learn. And then when it's exploding, it's the opposite. So partial E by partial omega, it will be very, very large values. So the gradient carry information used in RNN, and when the gradient becomes too small, the parameters updates becomes insignificant. So this makes the learning of long data sequences very, very difficult. And RNN uses a for loop to iterate over time steps of a sequence while maintaining an internal state, which is the memory that encodes information about the time steps it has seen so far. So I mean, in updating the weights, you can just imagine that RNN is running in a for loop where it iterates over the time steps of the input sequence, and each time step we try to just maintain the memory or updating the states. LSTM versus RNN. LSTM, it's a long short-term memory. It deals with these problems by introducing new gates such as input and forget gates, which allows for a better control over the gradient. I mean, RNN or vanilla RNN, it has a problem in vanishing gradient and exploding gradient, but LSTM, in fact, it has better design by introducing those gates, and those gates can give us much better control over the gradient flow and enable a better preservation of long-range independencies. So it's much better in terms of learning because of those gates. Those gates can help us to control the flow of gradient. So the long-range dependency in RNN is resolved by increasing the number of repeating layers in LSTM. RNN structure, I mean this is when we are just unfolding it over time. So this one, it's time, right? There are lots of structures like deep RNN, for example. So you can just have different layers, for example, can go more deeply, in fact. So feeding the output from one, I mean, we have this RNN here, and we try to update states, calculate outputs. So feeding this outputs to another RNN and so on. So in fact, we can go deep into this direction. We can call it deep RNN. Bidirectional, so we will go here in that direction, and bidirectional we go in the opposite direction, I guess. So starting from Y3, I need to revise those bidirectional RNN, in fact, but it's one of the forms which local versus global information, and each time you have those local outputs. So in each time step we update states. We start from initial state, so we have this local hidden state. We do it another step, we will get another local hidden state. We will do it until we get the last one, which is HN, for example. So HN, you can just call it its local hidden state / global hidden state. So maybe this is the most important. Maybe you are using only this one. If you will use only this one, we can call it the global output. So in each time step, you will get some output. We can call this output as a local output. And in the last step, we will get an output using all information from H0 until so far. we can call this one as the global output. You can use this one, or you can use all of them. If you use this one, we can call it using only the global output. And if you are using all historical values, it's historical values, right? If you are using those historical values, we can just say that you are using all local outputs. So, for example, you can use RNN here for predicting some outputs. And using this one for another fully connected layer for predicting a label, for example, or whatever, for classification problem. So in this case, if you are using only this one, which means you are using the global feature for classification, for example. So you will use the global feature for classification, only the global feature, which is the last updated output for classification. Or on the other side, also, you can use all local features. So you can just use local features, or you can use only the global features. Global feature, it's the last updated feature at n. But also you can use those historical values for classification. So this is how we use local features and the global features. In time series prediction, it's just we have an example from a time series, so we don't need to go through this one. But I can use the first value. For example, this is the first value in my time series. Here, the time window is 2, in fact. So I will use this first value. Yeah, so we have one time step. So the window is 2, in fact, right? So you have like a time series, and I'm just using each 2 values for predicting the third. So I'm using a 22nd. I'm using 22nd, 22nd, 23rd, 24th, 25th to predict 25th. And this is the first value which we're predicting, right? So anyway, yes. How can we use RNN APIs in Keras? So there are 3 built-in.
Can I ask a question?
Yes, please.
They have overlap, right? The local information has overlap on the last slide with the time stuff. And they have some kind of overlap in between like Y1 and Y2. We have 2 information that. In fact,
here we use the information at 22nd and the H0 for predicting 23rd, the output at 23rd, right? So if you have a time series like this one, so in the first update, I use the 22nd, right? And of course, I just started here. So this is the first data point, 22nd. I don't have any information from before. So I use the 22nd and I initialize the state with 0, for example, or random value. So I use the H0 and the 22nd for predicting 23, right? This value. And so this is the local value. So not global, this is the local value. And after that,
how can we use like this? Because we already know that 23rd, the actual value, and we have a predicted value as well. So how can we use this local information?
No, but we didn't use it. In fact, I mean, the most important for me is updating the state. So I updated the state here at 22nd. So I calculated H1 here, right? So I have here H1 at 22nd. So I will use H1 from 22nd with the input from 23 for calculating. I mean, just imagine that we are using it for calculating the output at 24th, right?
And so yeah, I get it.
So I will update the states here at 23. I will get a new. So at 22nd, I will have H1. At 23rd, I will get H2. At 24th, I will get H3, which is the most important here. I get here H3, right? So I will use. So I will 23, 24. So I can use this state H3 from all information from 22nd, 23rd, 24th for predicting the value at 25th. Correct? So the time window here, it's 3, right? So it's like the window has 3 values. So the input will be 3 values, a vector of 3 values. And I'm using those 3 values for predicting this one. So I'm using a 22nd, 23rd, 24th for predicting the output at 21st.
Yeah, I agree. Thank you.
So in Keras, we have very nice, it's very easy to use, in fact, but we need to practice. We need to practice it, including myself, in fact. We have LSTM layer. If you want to import it, you will import it using keras.layers.lstm. So if you want to use LSTM, you will import it from Keras. So you need to go to keras.layers, import keras.layers.lstm, and you need to import from here LSTM layer. And there is something called the gated recurrent unit, GRU layer. And the GRU, in fact, it's similar to LSTM without output gate. So GRU, it's similar to LSTM without output, right? Without output gate. So sometimes we are just interested in the states, right? So GRU, it's called the gated recurrent unit, and it's similar. I mean, if you want to import it, you need to go to keras.layers.gru. But GRU, it's exactly the same as LSTM, but without output gate. You know, LSTM has 3 gates, so GRU is a simplified version of LSTM without output gate. We have also simple RNN. Maybe the simple RNN, it's a vanilla RNN. This is very simple one. How can we get simple RNN or vanilla RNN? It's from keras.layers.simple-RNN. So this is simple RNN. If you want to just use RNN, so it should be simple RNN. We have also bidirectional layer. We have base RNN layer, conv LSTM 2D layer. So there are many things, but of course, for myself, I didn't use all of those. So, and maybe you will have maybe better time and to explore those in your work. So, what is the simple RNN versus original RNN? As I told you, this is RNN. So in RNN, we calculate the states, HT, using this function. This is the equation, in fact. You see this equation? So we use activation function hyperbolic tangent, and it will be omega x multiplied by x plus omega h multiplied by ht minus 1 plus bias. And apply the activation function to calculate ht, the equation. Now this is the equation here. We have this equation. So this is ht. So the states in simple RNN and RNN, it will be the same. Right? It will be the same, exactly the same. So this equation will be the same for updating the states. States are memory. This is very, very important. So the parameters will be the same: omega x, omega h, and the ph. So in case of RNN, we need to calculate the output. So the output will be calculated using softmax of omega y multiplied by h plus by. So this is RNN. But in case of simple RNN, the output will be calculated using just the softmax of the states directly without any weights. So the output here will be the softmax of the states, but the output here will be the softmax of the weighted sum of the states, omega multiplied by. So we will have here omega multiplied by h, omega multiplied by h plus bias, omega multiplied by h plus bias, and apply softmax to get the outputs. So this is the difference between simple RNN and RNN. So the number of parameters will be different. So if you are using simple RNN, number of parameters will be less than RNN. So the difference is that in simple RNN, the output is calculated directly using the softmax of the states, right? We calculate the output by directly applying softmax to the states. So this is the difference. We have here very nice example, but of course we can. This is time series prediction using RNN. I mean, the time series is simply a series of data points ordered in time. We know this time series. Data points are measured at successive equally spaced points in time. So we have the sample point, it's fixed. In time series, time is often independent variable, And the goal is usually to make forecast of the future, right? Time series is characterized by autocorrelation, seasonality, stationarity, for example. So there are some characteristics of any time series. We have this time series, it's airline passenger data set, and it's monthly data set in number of units of 1,000 to predict the number of international airline passengers in units of 1,000. So, for example, in January 1944, number of passengers was 112,000. The next month was 118. In March, it was 132,000. In April, it was 129. So this is the number of international passengers in 1,000. And it's monthly from 1949 to December 1960. So in total, this data set is for 12 years or 144 observations, monthly values. And the goal here is to predict or forecast the future number of passengers given the number of passengers in previous months, for example. So it's up to you to decide. So for example, you can just say that I will use yesterday value or last month's value for predicting current month's values, or I will use the number for this month for predicting the numbers for next month. So for example, if we are in January, for example, I will use this value for predicting this, and after that I will use this number for predicting this one. So the time window will be 1, right? If you can just someone else, he will just say, no, I will use the last 2 months for predicting the next month. So I will use January and February for predicting March. So in this case, we will have a bigger window, and it should help us to get better predictions, right? Because it will include those seasonality, stationarity, other values or other characteristics from the time series. Someone else will just say, no, I will use 3 months for predicting the number of passengers in the 3rd month or the 4th month. So I can, for example, now we are in April, correct? So I will use January, February, March, April for predicting next month, which is May. And then when we are in May, I will use those values for predicting June, for example, and so on. So in this case, the time window will increase. So you need to decide how many months you want to use for predicting n+1, right? We have in NLP, in the training, we used to divide the data into training and validation, training and testing, for example. How should we do it here in time series? Can you say something, Ali, about it? If I want to train if I will use RNN for making this prediction, I want to train my model, so I need to divide my data into 1 part for training, 1 part for testing. How should we do it in time series?
Can I say here?
Yes, please.
Mm-hmm. Yeah. So first we have to decide the what is it? The window. Mm-hmm. So for example, if we take window as many to 1, so 4 input respond to 1 output. So we'll split this whole problem into a supervised learning problem, and we make so first set of data will become, for example, the first 4 values, and then the 5th value becomes the output, and the first 4 values becomes the input.
Yeah.
And then we move the window a bit more. Then from 2, 3, 4, 5 becomes the input, and 6th month becomes the output. And similarly, we'll split the whole data into these vectors, so input and output. Then you can divide the whole data into how much you want for training, testing, and validation.
And okay, so we will split it first, and after that we will divide it into 1 part for training, 1 part for testing.
Yeah.
Yeah, but what should we do to avoid breaking the time dependency?
Sorry?
I mean, because should we shuffle the data? I mean, can we shuffle the data here?
No, we should not shuffle the data. Otherwise, the time. No, we don't shuffle the data.
Yeah, because if we will shuffle it, we will break the time.
The validation test.
Mm-hmm.
Yeah, exactly. We'll break the time series. Yeah.
Okay.
But,
so, for example,
I can show you an image which I made for the paper, which I'll submit for this class.
Okay.
And that shows this windowing index very well. I'll just quickly look for it.
So, for example, we can take from value or time step 1 or from the beginning to 80%, for example. The first part will be used for training, and the second part, the second block of data will, in the same order, will be, because we need to keep the order here. So the second part will be used for testing. Do you want to use the share screen or something?
I think if I can comment.
Yes, please.
Yeah, we can use the time step as an index, and then we can just assign the number of training we want, and we can go through each index sequentially and assign it as a training. Then for similarly for test and validation, but we should use the time step as an index to keep the sequence.
Yes, it will be an index, but it will not be an input.
Yeah.
Can you make me a host?
Yes, please.
Please.
Pirhan?
My name is Gaurav.
Okay.
Gaurav.
Okay, yes, sorry for. Yes, you can share your screen now.
Just for basic understanding, if this is the data we have for something, so we take this much window here as the input, and this becomes the output. So that becomes the first set of data to be given to the LSTM. Then we move the window a bit more, and that becomes input, output, input, output, input, output. So if we have multivariate data, for example, we have outdoor temperature, wind speed, radiation. So all of that becomes for n past time steps, that becomes the input, and the future after that becomes the output. And we keep moving this to split the data into these columns. And then we can split these lines as these rows of data as testing, validation, and training, or training, validation, and testing.
So maybe we can split the data first before data preparation, and we can do this for the training data and for the testing data, correct?
Yeah, yeah.
So first you need to split the time series into two blocks, one block for training, one block for validation, and after that you need to prepare your data in the same way.
Or you can do this windowing first and then split it. It doesn't matter.
Okay. Yes. So please, we will wait you for a nice presentation next week.
Yeah, I already made something. It's called sequence to sequence multi-input, multi-output LSTM model, but I can show it next time. It's nothing.
Yeah. Okay. This is great. Okay, so we will go back to our slide because we have only 10 minutes. So. Okay, so you can split or you can prepare your data first as many to one sequences, for example, or one to one. It's up to you. So someone is writing something. Okay. Okay. So this is my raw data. So it's just so this is my raw data. So we have number of samples. It's from 0 to 143 because in total I have 144 data points, right? So in my time series, I have 144 data points, and this is the number of passengers. So if you go one by one, if you go 1 to 1, for example, if it will be 1 to 1, so it will be, I will use the first value here for predicting this one. and after that I will use 118 for predicting this value if it is 1 to 1. So the input will be 1 and the output will be 1. But if you have a time window of n size, for example, of n features, if number of features will be 2, so in this case I will use the number of passengers at time step 0 and 1 for predicting it at 2. Correct? So I will use this one and this one for predicting this one. And after that, in the next step, I will use the number of passengers at time step 1 and 2 for predicting the number of passengers at time step 3. So it will be 2 to 1 or many to 1. So it's up to you. So imagine here that I'm using, it's 1 to 1 here. So I will use the time, I will use the feature at 0 for predicting 118, which is the number of passenger at time 1. So I will use this value for predicting this value. So this one will be 1 to 1, right? 1 to 1. So I'm using only one feature. The input will be one feature, right? So it's one feature, which is 112. And I will use this one at time step 0 for predicting the number of passenger at time step 1. And after that, the next step, I will use the number of passenger at time step 1 for predicting the number of passenger at time step 2, which is 132, and so on. So this structure or this data preparation, it's 1 to 1. If you want to make it, if you want to use two features, for example, so here we use two features, right? So in this case, I will use the values at time step 0 and the time step 1 for predicting the value number of passenger at time step 2, correct? And I will repeat this process. So now it's 2 to 1. In fact, it's 2 to 1. Or you can just say it's many to 1. Many to 1. So how many features you want to use? It's something which you need to decide, right? So after preparing the data should be at the end, it should be in the same structure here. It should be number of samples, number of time steps, times number of features, right? So how many samples? So time steps, it will be, for example, 2, and number of features will be 2, for example. So it will be like this one. So we prepare the data for training, right? So using this function, I mean this one I got it from online link. So just to prepare the data, look back here, it's the number of features or number of time steps, for example. And after that, I will use MLB for just I want to try to use MLB here, for example. So if I will use 3 features each time for predicting the fourth one, so I'm using 3. I mean according to here, for example. So I'm using the value at time step 0, 1, and 2 for predicting the number of passenger at time step 3, and so on. So in this case, number of inputs will be 3. If I'm using MLP, number of inputs will be 3, right? And I'm using 8 units in the first density. I'm using here MLP. So this MLP, it looks like this one. So I have here 8 units, and number of outputs will be 1 because it's a prediction, in fact. So it will be like this one. And how many inputs? We will have 3 inputs. So I will have X1, X2, and X3 connected to this one. So it will be like this one. So this one, it's MLP. So I'm using 3 inputs. I'm using 3 features or 3 inputs to predict the output at the next time step. So I'm using, for example, X0, X1, X2, in fact, to predict the output at X3. It will be like this. So it's like I'm using the last 3 days for predicting tomorrow values, or I'm using the last 3 months for predicting next month. So the time window here is, it has 3 values. So I use here MLP. Of course, the problem here in MLP, if at some point you want to increase, you change the window size, the model will explode. In fact, number of parameters will increase a lot. Because if imagine that I am using 4 inputs or 5 inputs, what will be the impact of the number of weights? It will has huge impact. I mean, at the moment, the number of weights will be 8 times 3, this one. In fact, it's 8 times 3 plus 8 equal 32. So this is the number of parameters. Number of parameters in the output layer, it would be 1 times 8 plus 1, so it would be 9. So this is and in dividing the data, I just divided it, that part for training, that part for testing. And this is my model. I use the mean squared error because it's a prediction. So the loss function here, it's mean squared error because it's not classification, but it's a regression problem. I want to predict number of passengers in next month using the last 3 months, for example. And I use the batch size equal to, and you can see this is the data set in blue, and this one, in fact, it's a prediction, the performance or the predicted value in the test set, the training set, and the green one, it's the predicted value in the test set. This is the root mean square error for training and testing. And you know the batch size, I mean, and when batch size equal to, it means we calculate the gradient for 2 values and we update 1 time each 2 examples, right? Using RNN, I used here simple RNN, and as I told you, in simple RNN compared to RNN, we calculate the outputs using the activation by applying the activation function. Yes, we will finish, Olga. We will finish soon. Okay. Thank you very much for today. Thank you. So we will stop here and we will go back again. We will start next week again from RNN from this example, but we will start by your presentation next week.
Yeah.
So just waiting for you. If you can send it to me, please, maybe before starting, so I can upload it to Blackboard. It would be very nice.
Okay.
So thank you very much for today. Yeah. See you next week.
Thank you.
Thank you. Bye bye.
Thank you. See you next week.
See you next week. Bye bye.
Sorry, can I have
Bye.